Great. It's my pleasure to introduce today's speaker, Stephen Briggs, who is the former head of Earth Observation Science, Applications and Future Technologies at the European Space Agency. He was the chairman of the Global Climate Observing System during 2013 to 2019. He is the assessor for the EU Copernicus CO2 emissions program and a visiting professor at Reading University and the Meteorology Department and at Cambridge in the Chemistry Department. He's also on the board of the Cambridge Center for AI for ER and has been working on satellite observations for climate studies for, he says, more years than you would care to remember. But I think it's fair to say he knows a lot about this. And I'm looking forward to an absolutely amazing talk. So thank you so much for taking the time, Stephen, and it's all yours.
Thanks very much, Keshav. I gather can you hear me? Yeah, okay. I assume you can. Well, thanks very much for the opportunity to talk to you. And today I've decided to talk about one particular aspect of climate, which is greenhouse gas emissions and how satellites can help support the Paris Agreement and the emissions agreements which will be made under that. And before I start to talk about that, I think it would make sense to try and just give you a very short video which shows what the scope of the problem is and shows quite how difficult it is. So I'm just going to show this video, which is a simulation of CO2 concentrations in the atmosphere over Europe over 1 month of 2008. So what you're seeing here is anomalies above the mean. So the mean value is white on the right hand side, and then you have anomalies of parts per million of up to plus or minus 5, red and blue in each area. And you see the emissions from fossil fuel emissions from the major power stations in Pronerav and Procciaderi near Cologne, from Jürgenswalde and other places over Europe. And they are combined with the emissions and absorptions which come from terrestrial biosphere over the continent. So the problem is that it would be nice if we only saw the fossil fuel emissions, which we're interested in, but we don't. We see everything that's in the atmosphere. And that includes the emissions and absorptions of CO2 from the atmosphere that we get from, in particular, absorptions that we get from the terrestrial biosphere. And so you see blue areas, which are essentially holes of CO2, if you think of it in that sense, reduced amounts of CO2 in the atmosphere, which have been removed by the activity of vegetation, green material on the Earth's surface. And so we have to be able to untangle the various different components of this as we see it. And you can see these are quite considerable, and here you see a major swathe of CO2 absence, if you like, being driven across Europe. And this is all integrated with an integrated forecasting system which tells us about the meteorological conditions and the atmospheric dynamics. So somebody has once likened this to trying to take the milk out of your coffee, but really it's much more difficult than this. It's taking 198 cups of coffee, putting some milk in each of them, then tipping them all into a big bucket, and then extracting a molecule of milk out of that and telling you which cup it came from. So it's quite a difficult problem, and it's compounded by the fact that the Earth is not a passive bystander in all this. So we'll move on to recover my pointer. We move on to an overview of what I'll talk about. So we have atmospheric concentrations, which is what we see in the atmosphere. Remember, we don't see emissions, we see concentrations. We see the result of emissions. So we need to understand the processes to be able to predict how CO2 is injected into the atmosphere and consequently what the effect that has on climate change. Mostly, and until recently, CO2 measurements came from local stations, in situ measurements, and these need to be integrated with the models. But we now are able to begin to measure from space concentrations of CO2 in the atmosphere as well as some other greenhouse gases. And that's helping us to improve our global perspective. So what we see here, the carbon cycle in the sort of Disney version. So you've got carbon being emitted from the oceans, absorbed back into the oceans, absorbed by the terrestrial biosphere. We have emissions from fossil fuels, from volcanoes, from biomass burning. Eventually, CO2 disappears, if we're lucky, into ocean sedimentation, and it goes down into fossil fuel or fossil relics into the soil, coal in the soil, which if we don't burn it, they're the only two permanent reservoirs of CO2 on Earth: ocean sediments and essentially coal. So providing we don't burn the coal, then it's a good thing. If we put some numbers on that, then these are the net flows of CO2 in gigatons of carbon a year, gigatons of CO2 a year. So fossil fuels give us about 34 gigatons of CO2 a year being emitted into the atmosphere. Of that, the biosphere absorbs about 13, terrestrial biosphere. The ocean absorbs about 9. Land use change also contributes to, talk more about that a little bit, into the emissions which we see as well. But the important points are, I'm reluctant to move my pointer because it makes my screen shift around. You'll see that from the vegetation you have an increase, you have an emission and an absorption from terrestrial vegetation of about 440 gigatons of carbon per year, and the same in the ocean. So the fossil fuel which we see in the atmosphere, fossil fuel CO2, the anthropogenic CO2, is superimposed on this large emissions and absorptions which are coming from the terrestrial biosphere. Now, the fact that they cancel themselves out is very good, so it's effectively neutral within about 1% anyway. But of course, the problem is that the absorption and the emission doesn't necessarily occur at the same place and at the same time. So the respiration of CO2 doesn't occur at the same time as the absorption. Sorry. So we see in between CO2 being respired and it being absorbed somewhere else, it appears in the atmosphere. And if a satellite passes over, then it sees it. So we have to be able to extract that from the main signal. And this is another way of looking at it. If we look at the evolution of emissions over the years, then you can see on the top half of this shows you where the emissions come from, mostly from fossil fuels and industry, and about 15% or so from land use change. And where does it go? It goes into absorption by the land, absorption by the ocean, and the bit that isn't absorbed accumulates in the atmosphere, and that's what we see as the increase. And over the years, you see the combination, the difference between the fossil carbon emissions and emissions as a result of land use change. And these are the only two components which are considered for anthropogenic emissions by the IPCC and by the UNFCCC and the Paris Agreement. Where does it come from? You're probably familiar with this. Most of it comes from China, but there is a slight amelioration of that by the fact that their land use change CO2 emissions are actually absorptions. So clearly, if you grow more forests, for example, than you destroy, then you will have a net sink of CO2 into your country, and you see the comparisons between them there. And the net effect of all this is that we've had this trend of CO2 increasing the atmosphere from about 270 odd parts per million in pre-industrial times up to today about 420 parts per million. So it's about a 50% increase over the last 250 years. What's the effect of that? Well, everybody used to talk about global warming, but thankfully we're beginning to think that there's a little bit more to it than that. And this, when I was chairman of GCOS, we wanted to try and get a more complete picture of what the increase in carbon was doing to our planet. And so we tried to find a number of global indicators of climate change, which would be a little bit more comprehensive in its description, rather than simply talking about global warming. So we have here from the top left, you have ocean mean temperature, which is our global warming. We have atmospheric CO2, which is a necessary indicator, if you like, of the changing atmosphere. But we have a few others as well. So we have ocean acidity, shows us how the ocean is becoming more acidic by the dissolution of CO2 into seawater to make carbonic acid. We have the loss of ice in the land glaciers on the top right. We have the ocean heat content on the bottom left, which I'll say a little bit about. We have the increases in sea level change as a result of ice mass loss from the ice sheets, thermal expansion of the oceans, and loss of land ice glaciers, and extent of sea ice in the Arctic and the Antarctic, which is, particularly in the Arctic, is decreasing very rapidly. And you see the particular troughs in 2007 and 2012. And the predictions are that if we continue at this rate, then we would reach an ice-free Arctic in late September, which is when it reaches a minimum, by sort of sometime in the middle of this century. So these were very nice pictures, and they were adopted, in fact, by the WMO. And if you go to any UNFCCC and WMO publication, you'll see these now as the official sort of WMO indicators of climate change. The one I think is very interesting is the ocean heat content. We could talk for half an hour just about this, but this shows where the energy, which we talk about global warming, well, where does the energy go? And you see it goes almost exclusively into the oceans. So the different depths of the ocean between 0 and 700, 2000 and below 2000 meters gives you the three-colored blue on the right. Then we have how the land warms up in Siena. Then we have ice, the cryosphere in grey, and the atmosphere. So when we talk about atmospheric warming, there's clearly very little heat energy which goes into warming the atmosphere because the atmosphere is not very dense. And so although the temperature may rise, the heat capacity is very small. It's a bit like the solar corona. The solar corona is at 2 million degrees, but if you put your hand in it, you wouldn't burn because there's almost nothing there. So what you're seeing here is that the ocean is really the main area that's where the heat is going. And that causes thermal expansion as well, and that's one of the main components of sea level rise. About a third of it comes from ocean expansion. There's a number of things to say about this. Firstly, it's a very clear secular rise in energy composition of the Earth. Secondly, so we have a monotonic increase essentially. The actual size of it, the units are in zettajoules, which doesn't mean much to me anyway. It's 10 to the 21 joules. And roughly speaking, we have an increase over the last 50 years of about 5 zettajoules a year. And that doesn't mean much either until you think that the entire production of energy by mankind, by all forms, fossil fuel burning, but also all renewables in transport, in nuclear fusion, nuclear fission, and everything else. So the entire energy generation of mankind is about half a zettajoule a year. So the Earth is absorbing 10 times more energy per year than mankind generates. And I was once giving a talk, and there was a climate denier there who said it was all due to the Russians letting off atom bombs in Siberia in the 1950s. And I pointed out that the increase in energy is not a term or a comparison I like to use. Is equivalent to a Hiroshima atom bomb about every 2 seconds. That's the amount of energy that the Earth is absorbing. I mentioned briefly sea level rise, and one of the nasty effects of sea level rise is it's not homogeneous and isotropic. And what we see is a very rapid, very large changes in sea level rise over the distribution of the globe. And we see for North America, for example, sea level is actually falling off the western California coast. But if we look in the Southwest Asia, and when I gave this talk once, or a talk including this slide, and the next speaker was the head of the Met Service from the Solomon Islands, which is pretty well in the middle of that red blotch you see to the east of Papua New Guinea. And there you see that the rate of sea level rise is not 3 millimeters a year. In fact, actually, it's about 4 on global average these days. But it's something like 4 or 5 times that. So we're seeing, unfortunately, it's a really horrible coincidence that those areas which are most susceptible to sea level rise are actually the ones which are seeing the worst sea level rise just from a physical basis in their region. Anyway, moving on to greenhouse gases and satellites. So we have a challenge when we can from a satellite above the atmosphere look down and see something about the content of the different greenhouse gases in the atmosphere. The trouble is we see the impact of emissions, which in other words, we see the concentrations. We see what has been emitted and remains in the atmosphere. So we have to find a way of translating from concentrations at a given point in time and space to emissions at some previous point in time and space. And that is really where the problem lies. And it is an immensely complicated and difficult problem. So we've been able to do this sort of measurement since about 2002, and this goes back to an instrument called Skiamaki, which was flown on Envisat, which was the largest environmental satellite ever built, and ESA's really most important satellite. It was launched in 2002 and continued in operations until 2012. And this shows a global composite of maps of NO2, which was constructed from the Skiamaki record, and shows wonderful concentrations of the gas over the urban centers globally. And this picture appeared on the front page of almost every newspaper in Europe on the day that it was published back in 2003. And I happened to be traveling across from where I was working in Italy at the time to a meeting in the Netherlands. And I saw all these newspapers, and this, as a result of this publication, the Netherlands government became somewhat alarmed, and they actually funded, it's a long story, but eventually they came to fund an instrument called Tropomi, which is now flying and measuring details of nitrogen dioxide in the atmosphere, currently on a series of satellites, and will continue to fly on Sentinel satellites into the future. So this spurred one government specifically into action. But you can see actually individual cities picked out here. You can see Moscow, for example. You can see Johannesburg and the Johannesburg area, Pretoria in South Africa, Rio de Janeiro and Sao Paulo in Brazil, and so on, and whole areas of northeast United States, the Benelux and southern England, and northeast China. You can see there very clearly. So you can clearly pick up these measurements in space. The question is, what do we do with them? And since that time, we've had a range of different sensors which have been built. The Skiamaki was the very first. That didn't look at CO2, but looked at other gases, NO2 and methane. We've had since then Japan, China, the US, and increasingly Europe has been building different satellites over the years, which are being able to look with various different capacities at carbon dioxide. They're being increased all the time, and there are a number which are under development. Merlin is a particularly interesting one because this will use a laser system. Most of these use passive remote sensing, so they're looking at reflections from the Earth's surface of sunlight through the atmosphere and picking up on the spectroscopic signature of the molecules in the atmosphere. Merlin will actually use a LiDAR system to probe down into the system, into the atmosphere, and pick up methane concentrations. That's a sort of holy grail to be able to do that for CO2, and there have been proposals to do that for at least 20 years that I know of, and it's just not technically feasible at present. So we are able to make these observations, and increasingly in future we'll make them. Now, how does that relate to the overall process? Now, this is where it gets a bit complicated in terms of the way that these are assessed under UNFCCC rules. We have this whole process of the Paris Agreement, whereby countries have to provide national greenhouse gas inventories and report on these on a biennial basis into the COPs. They can be constructed in different ways, and I'll talk about that in the future, but essentially they bottom up. So you add together for the fossil fuel emissions, you make a very detailed inventory of all the fossil fuel which you burn in your country, and the conditions under which it is burned, the temperatures at which it's burned to the products which are generated, and you do that for all your different fossil fuels, coal, natural gas, petroleum, and so on. And that becomes your input into the national determined contribution. There's a second component, as I touched on earlier, which is what's called AFLU, Agriculture and Forestry and Other Land Use, or sometimes LULUCF, Land Use and Land Use Change in Forestry, which essentially says that if you transform land use from one category of land use into another, from cropland into forest or from forest into grass or whatever it may be, there's a limited number of categories, then for each hectare of land which you convert, there is a number which you should associate with the CO2 emissions or absorptions which are related to that particular hectare. And so you have area totals for these different types of cropland or pasture land, and you have emission factors which are applied to each hectare. And that gives you the second component of anthropogenic emissions. And this is in the case of managed land, and under the auspices of the UNFCCC, almost all the world is managed. The whole of Europe is managed, the whole of USA is managed, even the wilderness. So you have the curiosity of there being managed wildernesses in the US. Virtually the whole of Canada and Russia. The only bits which aren't managed are, I think, the whole of Congo, I think the only parts which aren't managed are parts of the northern tundra in Russia, bits of northern Canada, and a few bits of the Amazon, but even most of the Amazon is regarded as being managed. So the whole world is more or less managed. They then have to report these on a two-yearly basis, and each time they report on their nationally determined contribution, their inventory, each country has to say what they're going to reduce that to in 2 years' time. And they're not allowed to go up, they're only allowed to reduce. This is what's called the transparency framework, so you have to try and find a mechanism to ensure that everybody has a full picture of what's going on. And then every 5 years you have a global stocktake, which looks back and says, is everything we're seeing consistent with what we're seeing from each of the individual contributions? And that's then assessed by the UNFCCC. And the Secretariat, and the picture you see above there is that's the UN building in Bonn, which used to be the German Parliament. It's now part of the UN city in Bonn, where the SubSTA meetings, the subsidiary body for scientific and technical advice, which advises the COPs, meets twice a year. So it meets there every June, and then it meets again at the same time as the COP in whichever location the COP is located at. You can also do that same process top down and measure from satellites what you're seeing in the atmosphere and how much that atmospheric concentration has been increased and the location of that. Now, for the total global concentration, you simply need to make a measurement at Mauna Loa, and at that point you simply see the CO2 going up. But from top down, that gives you the global total. But what you would like to know is to have some regional differentiation of that and to understand where those emissions are taking place. And that's what we're striving to be able to do. Now, the intention of this might be, if you think in a simplistic sense, to have some sort of global police verification system imposed on countries by an integrated spaceborne system, if that were possible. And then they would all have their fingers wagged at them, and they'd be told they'd have to do better. I think if you were to, even if you had the capacity to do that, which we don't at present, I think the UNFCCC would run a mile from it, because they're not in the business of trying to enforce limits on countries. They're there for a cooperative process which will move forward with an overall reduction. It's a little bit like the discussion you probably will have heard about this at this COP on loss and damage. Loss and damage is something which is well accepted, but you must not use words like compensation or liability or reparations. And member states, the developed countries, are on the whole happy to contribute to loss and damage, but not if you insist on calling it a reparation or so on. So one has to be, the language is absolutely all important in the COP process. And I'm not going to say too much about COPs. I'm not going to defend or describe whether they're good or bad, but it's a process which has to be handled by kid gloves is an understatement. It's an extremely sensitive process. And what we want to be able to do from satellites is to help contribute to an assuredness that the integrated NDCs which we get from each of the countries all hang together and make sense, and that we can agree on what the overall path is. Now, the way that things are done at present, this is a bit complicated, but it's useful to know. Traditionally, these inventories have been created by the bottom-up inventories, which I talked about. So you add all the fossil fuel inventories, shown in white there, and you have the land use disturbance with emission factors. You can integrate those in many different ways. How you do this is a 9-volume document. Each of the volumes is about 1,000 pages, written by the IPCC Technical Support Unit in 2006, modified in 2019. It's extremely conservative, uses quite low technology. Why is it people only ever call me when I'm doing this? Uses quite low technology for very good reasons, so that it can be repeatable and transferable across the world. That's all well and good, but it's not particularly accurate. And there are many different approaches there are three different approaches that can be done for land use, which is using a sampling system where you look at the conditions for 1 square kilometer every 100 square kilometers or something like that. Or you have a survey which gives a sort of agricultural survey of what your land cover is doing at any given time. Or you can have a mapping approach, which is clearly the one which is most sustainable, most transferable, repeatable, verifiable, and can be based on satellite data. So you have an annual or biennial, whatever is needed, cover map for the particular classes of interest in your country, and you have that, and then you compare that with the previous map. You look at the changes, you apply the emission factors for those changes, and that gives you your land use emissions. That uses paper-based emission factors, but that then gives you a number which says that for every hectare of wheat that was, or cropland, it's not even wheat, it's cropland, which is converted to forest, then this is the number you should apply. That can be more subtle depending on what type of forest it is, what type of trees are being grown, and so on, but it can be as crude as just the 6 classes. And what we would like to do from satellites is actually to be able to, rather than give a paper number which is prescribed for every type of land cover transition, we would like to be able to give a number which is actually measure the change in biomass. Now, you had a talk a week ago from someone who was talking about the ESA biomass mission, which I was very much involved with in its early stages. And that will be very important in estimating very high levels of biomass in humid tropical forests. It's unique P-band mission, so it's got very long wavelength, 81 centimeter wavelength. And it's the first mission which will be able to measure the biomass of tropical forests up to the limits of where they are. Previous missions saturated about 100 because of the nature of it's essentially the frequency of the radar. They saturate at around 100 tons per hectare, whereas tropical forests will go up to 400 or 500 tons per hectare. And P-band will allow you to be able to measure all the way up to that humid tropical forest limit without saturating. So it's a very important mission, and that will help to look at the changes in biomass in very high density forests in the tropics in particular. So that's the way things are done at present. You have the fossil fuel inventories, which are bottom up as well. Those are delivered into the NDCs and to the Global Stocktake, which takes place every 5 years, and then that progresses into the future. What we would like to see is to be able to augment that by using satellite data. And you see in the bottom pinker box, you have a series of satellites, GOSAT, OCO2-3, Sentinel-5P, and so on, from the Committee on Earth Observation Satellites, CEOS, which provide measurements of CO2, CH4, NO2, and other gases in the atmosphere. But in order to do that, you need to be able to model the terrestrial biosphere. So you have to have digital dynamic global vegetation models, DGVMs, and they require all sorts of other data to drive them. It could be data such as surface temperature, maybe solar-induced fluorescence, soil moisture, biomass, leaf area index. Depending on the model, there could be a whole range of different parameters, together with meteorological parameters, which could be on an hourly basis, things like humidity, air temperature, and so on. We also have, from the World Meteorological Organization, coordinates integrated greenhouse gas information system, IG3IS, which looks after all the global measurements of in situ greenhouse gases using flasks and towers and so on, of which there are several hundred. So those are all backing systems which allow us to improve the estimates which we can make from the bottom-up system. And there are integrated, so-called integrated MRV systems, monitoring, reporting, and verification, which are being designed and built in Japan by the National Institute for Economic Environmental Systems, NIES, not NES. The carbon mapping system in the US, which is a bit less integrated, and in Europe, something which I'm very much involved with, the Copernicus monitoring verification system, which is a very well integrated system being developed, led by ECMWF in Reading, but involving a consortium of scientists all around the world. And this is part of a wider Copernicus CO2 monitoring system, which includes the development of several satellites and a number of services based on this. So it's a fully integrated space-based in situ measurements, modeling, plus an inversion system, a 4D VAR inversion system, which I'll come to. So now you know how these things are done. Let's go back and think about what the consequences might be. We'll see that in a moment. So this is what essentially this is a block diagram for how the Copernicus system works. So in terms of observations, you have the satellite measurements we talked about. You have the in situ measurements and airborne measurements of CO2 and methane. You need to know the in situ meteorology and also data from satellites, and then the various different auxiliary data which you need, including data about the terrestrial biosphere. You have prior information which comes from model fluxes, and that's quite interesting. I'll come back to that in a moment. Emission reports, economic statistics, and all the bottom-up inventories. And then you have to put that into a system which allows you to eventually invert that whole process and come out with a series of CO2 and CH4 emissions, country emissions, and other products. So that's all you have to do, simple. And if we look back now, if we try and think about how you do this, we go back to our original slide. We just have another quick look at that. So this is what you're trying to model, and you've got all these different types of measurements. You've got models of the behavior of the terrestrial vegetation. You have an understanding of the numbers coming from fossil fuel emissions. The trouble is that these are not necessarily all on the same basis or the same spatial scale. If you take, for example, in the Netherlands, or all countries provide a number for transport emissions, but they don't tell you where they come from within the country. So since we have a geospatially disaggregated model here, we need to know where within the Netherlands those emissions are coming from, because it's being modeled on a four-dimensional basis. And so TNO in the Netherlands has essentially disaggregated their national emissions of transport on the basis of whether they come from road or rail, and then they assign them to the geographic locations of the main road and rail routes. So there's a reasonable estimate of how you can distribute the transport emissions according to the road and rail networks in any given country, which gives you that sort of geospatial distribution and disaggregation. So there's a lot of thought goes into understanding how you prepare these bottom-up estimates. Okay, so now you can go back, and now you know a little bit more about how you do it, and begin to appreciate just how impossibly difficult this is. Not impossible, just very difficult. And this is now what's being developed at ECMWF. The IFS is their integrated forecasting system, and there what you have is a 40 var atmospheric inversion which ingests all the data which we get from the satellite data. It builds in the emission inventories coming from the national inventories. It builds in models of vegetation and distributions and ocean fluxes which come from various different sources. The ESA Climate Change Initiative produces a global 1 kilometer resolution land cover map every year. JRC, the EC Joint Research Centre, produces something similar. And the output of all this would be, if everything were to be perfect, would be an inversion which tells us where all the emissions are coming from. Now that's very difficult to do when you only have very small samples. If you go back and think about that highly variable in space and time distribution of CO2 in the atmosphere, then understanding how you reconstruct that from very intermittent, very partial observations from satellites is really quite a difficult job. But it's a classic question in some respects in how you reconstruct reality from an imperfect sample of information. And this is the CO2 program within the Commission. So it started off with 3 reports, an overall report called the blue report in the first one. The second, the red one, is about satellite observations. The green one is about in situ measurements. And there have been a number of research programs, beginning with CHE, what's that stand for? Carbon something in Europe. And then something called COCO2, which is the research program now, which is putting together all the different parts of the emissions observations from the ground and the concentration observations from satellites. And hopefully this is going to contribute to the first of the CO2 European Sentinel satellites will be launched in 2025. in time to be able to contribute to the 2028 Global Stocktake, for which data will be gathered from 2026 on. So this would be a European integrated system for providing global estimates of emissions based on satellite plus other data down to at a national and subnational scale. Doesn't sound much, does it? So these are the sorts of observations you get from GOSAT or from OCO2. OCO2 is the Orbiting Carbon Observatory, which was launched by NASA. There's an OCO3, which is now was made up of the spare parts from OCO2 and is put on the space station. So we get increased coverage now between latitudes plus or minus 52 degrees. GOSAT is a different type of system. It gives you lower resolution but more frequent coverage. So they are quite complementary to each other, and you see the sort of data you get back from them measuring concentrations. But then the trick is to go from concentrations to emissions. There are also ground-based systems, as I mentioned, the ones from WMO, and there are also aircraft and ship-based measurements, so this is why you see these trails. Japan Airlines aircraft have been carrying for many years CO2 sensors in their nose cones, and so you get flights wherever Japan Airlines is flying, you get these lines around Tokyo, back and forth from Tokyo to Sydney, for example, and you get ships of opportunity across the ocean which are carrying similar sensors. The fixed points in red is the usual highly irregular distribution of flux towers and other local CO2 measurements. These sorts of things, as in all meteorology, are always focused on the developed countries, and places like Africa you see have something like 4 or 5 CO2 towers, whereas France will have about 6. That's always a problem. And then that allows us, even without the satellite data, one can constrain the inversion models using just the ground-based data sets coming from the towers and so on. And these are some of the results which come from some work that's been done by Philippe Pellin, who is contributing to the overall Copernicus system as well, who's very good in working in this for a long time now. And it shows the sorts of emissions that one can predict coming from the integration of vegetation models, global models, in situ data, and inventories. You can do the same thing from inversion models constrained by space-based data, and you can achieve not only the CO2 concentrations, but also the gross primary production and net biosphere exchange and so on, and other aspects of the behavior of the terrestrial biosphere related to the CO2 emissions and absorptions. This is a clever slide which shows in that long thin stripe going down the middle, that's a track of OCO2, which is passing over a very large power station in South Africa. The power station is located on the right-hand side under the cross. And what you're seeing, if you blank out the background for the moment, what you're seeing is a concentration of CO2 in that track as you're heading south over the point you see where it's bright red. That's not where the CO2 is coming from. It's coming from the power station to the northeast, but it's crossing over the track, over the plume, which is coming from that power station, is drifting west-southwest, and you're picking up some of that with the CO2 track, with the OCO2 track. But we also have a satellite Sentinel-5 precursor, S5P, which has a much broader swath and measures the NO2. And the two are co-emitted. NO2 and CO2 are co-emitted by the power station. So the background image you see with the wider swath and with the long plume is actually showing NO2 distribution, and we can only measure CO2 in that narrow swath which comes down. But by combining the two, we can make some estimate of the NO2 which is contained in the entire swath from Matimba down to the southwest. So by combining low resolution, wide swath observations of co-emitted species, one can get a greater distribution for the CO2 observations as well. So this is a nice way of combining different types of measurement. And I'll come to the end. I just mentioned briefly And this is a comparison between atmospheric inversions and the data which we get from AFLU inventories being given us by the various different countries. And sometimes you see that they agree very well, and sometimes you see that they don't agree very well. The constancy of the numbers being given by countries suggests that they don't do it as carefully as one might. You might not expect to have quite such completely consistent estimates of AFLU as you might get here. And the values we get in the green are the inversions that we get from the model data. So in some cases they're in good agreement, in some cases they're not in such good agreement. In Canada, for example, not at all in good agreement. There's probably a much bigger sink of CO2 in Canada from their forest than they think there is coming from their AFLU data. So this shows us the difficulty and the discrepancy sometimes between different methods. I'll mention briefly methane, not because it's not important. It's equivalent to about 25% of the warming potential of CO2, because although it's less concentrated in the atmosphere by a very large fraction, it's per molecule it's much more. It gives this warming potential is much higher, 80 times that of CO2. We can do the same sort of budget for methane. At the moment, methane comes from a number of different sources. It comes from fossil fuel emissions, it comes and leaks from pipelines, it comes from enteric methane from animal husbandry, and also from natural loss from warming, permafrost and so on, and for other forms of agriculture. As an important source, about 35%, 40% comes from oil and gas installations. And there's a big drive at the moment because these are easily seen, to look at these. CH4 is very easily measured. Methane is much more easily measured than CO2, particularly when you're looking at sources like this, which have very low background. There's basically no methane emission from the areas around them. This is from Central Asia, but a lot of work has been done in the Permian Basin in the southwest United States. And there you can very clearly see what the emissions are. And there are various different initiatives working with the fossil fuel companies, because some of these emissions are not deliberate, they're simply leaks. And quite a lot of the methane coming from fossil fuel companies is actually inadvertent leak. Some of it is also burning off and coming from the fossil fuel sources themselves. And there has been an initiative by the Biden administration to bring to bear, based on these sort of satellite data. This comes from a private company called GHGSat, which provides its data to the science community as well, which essentially is working with fossil fuel companies to reduce their emissions under an overall government program enforced by the Biden administration. So there's a lot of work going on there, part of that due to Al Gore, and an organization called Climate Trace, which is heavily involved in this. And we can compare the emissions that we see from methane. I'm nearly finished, but methane is much less well known from its inventories than CO2, that's all I'll say. We're unlikely to get much improvement on the UK CO2 inventory from satellite data. It's probably accurate to a few percent already, whereas methane is probably no better than 30%. And already the UK, Switzerland, New Zealand and Australia are using satellite data to improve their methane inventories, even in the most developed countries. So there is promise in all this. I was
from
above
Earth, satellites.
I won't go through, that was another video I was going to show you, but I'll just come into one last point. At the moment, one question is, what could AI do to improve all this? Well, you've seen essentially how you put together the emission models. It's from a whole series of observations. The vegetation models that you get from the Earth system models, you put them together in a simulation scheme, and out of that you get emissions. It's very complicated and very difficult because all these models are extremely complex. They all require vast numbers of parameters, and they all have a lot of geophysical uncertainties in them. It may be better, nobody's done this completely, but you could think about doing this in a machine learning perspective, where you simply have your observations and your known emissions, and you use an approach. And in fact, this is how the priors are set for the CO2 global vegetation models is set by a random forest approach to modulation of the in situ measurements of the CO2. So parts of this are being integrated already, but you could think about doing this in an entirely machine learning fashion. Nobody's done that yet, and I think at the moment you wouldn't get a better result, but maybe one day. So instead of having process-based physical equations which tell you about the behavior of the geophysics of what's going on, then you would have a data-driven system based from all the measurements that you've made around the planet. And there are some examples where AI is being used in this. When we looked at COVID lockdowns of nitrogen dioxide emissions over Europe, these were the routine measurements before and during lockdown and the changes which occurred. And these were then improved by applying machine learning with the meteorological data to be able to get more accurate emissions which respond more precisely to just the single driving forces we're interested in. And one could think about using different types of data as well, from activity data, energy statistics, weather data. And this is how that was included to look at the methane emissions for COVID-19 to try and improve the estimates that we get from the raw measurements which we make. So trying to bring in other forms of knowledge into that simply extrapolating from the observations that we have. So there are the beginnings of integration of machine learning into some of these components. And in fact, we had a presentation in the CDT series last year from Martin Jung from MPI in Germany, who is the person who provides the priors for the global vegetation emissions based on a random forest technique applied to the local measurements, coupled with about a dozen parameters which describe the meteorological and vegetation status across the world. Anyway, that's enough for now. I've run over a little bit, but there's still a few minutes left. So thank you very much for your patience.
Thank you so much, Stephen. We do have time for questions. If you have a question, please unmute yourself and ask. While people are thinking, Stephen, maybe I can ask you one question. I think the video you started with looked very impressive. Presumably, it's based on some kind of simulation that has all the detailed models that you talked about already. When you talk about the AI-based approaches and you're looking at observations going back to the possible sources of emission, do you feel that these models would be used? In other words, would it be purely data-driven, or would it be constrained by some aspects of known models?
Well, in fact, for the Copernicus inversion, they have two models for vegetation. One is for Europe, and one is for the global regime. For Europe, they use a prescriptive vegetation model called VPRM, which is quite an old model now and not one I like very much, but it's used on a 1 kilometer resolution scale. It's driven by a couple of numbers taken from satellite data, which are characteristic of vegetation activity and of moisture in a way which is not very transparent. And they use that together with hourly measurements of rainfall, insolation, air temperature, soil moisture, and a number of other things. And that generates a model for the behavior of the biosphere, and then that's integrated. That's what provides the CO2 fluxes for the European continent. For the global system, they use almost an entirely AI approach. So they don't have a vegetation model. They take the 400 and something measurements which are of in situ CO2, and you say, how would you distribute the global CO2 from these? And simplistically, you could say, okay, we'll just interpolate. That would give you an answer, but it wouldn't be a very good answer because it's highly conditioned by the distribution of vegetation. So they use about 10 parameters to condition the distribution of CO2 on which using a random forest basis. So the constraint is essentially the original emission measurements or absorption measurements, concentration, sorry, which are measured by the CO2. And then that's conditioned by these 10 or so physical parameters about the status of the environment and the biosphere, the atmosphere, and so on. And they are optimized using a random forest technique to give you the global priors. And that's what Martin Young talked about in one of the CDT seminars last year.
Great, thank you very much. Any question? Anybody else have a question?
I have a question. So we talk a lot about satellite data, but how much effort are people putting into expanding these global on-the-ground sensor networks? And what are the difficulties in doing that, especially globally? And what are the pros and cons compared to satellite solutions?
Okay, that's a good question. That was several good questions. The big problem for these measurements, as you saw and I mentioned at the time, is that they're highly concentrated. They're mostly made by Met services, and they're highly concentrated on the Met services of the richer countries. So you have a lot of duplication, or perhaps one shouldn't say duplication. There's no such thing as too many measurements. You have a high concentration of measurements in richer countries and very few of them in poorer countries. That's a problem for all meteorology. And in fact, it was shown recently that the most important radio sonde observation for numerical weather prediction is one which is set off in the southwest Pacific off one of the small islands there. And so there's now been approved a scheme called GBON, the Global Basic Observation Network, under the WMO, funded by the Green Climate Fund, to improve the network of observations, particularly for CO2, globally, and particularly to fund those countries that don't have the infrastructure and the wherewithal to be able to provide those sorts of global measurements more readily and better distributed. I chaired a 3-day workshop with the WMO in May of this year to set up in place a global greenhouse gas monitoring system, and there's another workshop going to take place in January. And the bid will be going into these funds to be able to increase the distribution of in-situ measurements of CO2 and other forms of meteorology, but in this particular case of CO2. So something is being done about it. It won't be perfect, but it's a well-known problem, very well-known.
And are developing countries open to having these sensors installed?
Yeah, they're desperate for them. They're very keen to have them. It's the same as they're always very keen to come to WMO and to global funding sources to be able to improve their national meteorological networks, whether that be for CO2 or for other things as well. And they probably stand most to gain in terms of the improvement of their national inventories. I said that for methane inventories, even developed countries, UK, Switzerland, have derive significant benefit from having satellite ingested data into their inventories. I know of one case, and that's Mongolia, which used data from the Japanese NIES inversion system to improve their national inventory for CO2. I suspect that's because the original CO2 inventory from Mongolia was probably not as accurate as some of other countries, and therefore even a single data point coming from the Japanese system was able to improve their knowledge of their emissions.
Mm-hmm.
As we put more and more satellites in place and build up the expertise in the inversion and so on, then this would be something which could be, I think, of significant benefit to particularly countries which don't have a very sophisticated inventory monitoring system locally to improve their national contribution assessments.
Okay, that makes sense. Thank you.
Oh, Harriet, do you want to unmute yourself?
Yes, thank you. A fantastic talk. Thank you very much. You showed us some, I think a picture of about 20 samples, including Kazakhstan and Mongolia, which I would call a kind of an error, in layman's terms, an error or variance.
Yeah.
And I'm just wondering how much does land use, and particularly tropical forest, present that error? And is it statistically important? Is it significant in terms of the degree of error for other measurements?
Yes, it's not the driving force. As if we go right back to one of the early slides, typically of the anthropogenic emissions from a country, something like, or globally, let's say, not for each country, globally, the anthropogenic emissions can be split into two components, the fossil fuel and the land use change. Fossil fuel is about 75–80%, something like that, of the total, 85%. So it's about 5 times the size of the component which comes from land use change. Now that would be different in different countries, of course, as I showed in the case of where the most emissions are coming from, sometimes that land use change is an emission, sometimes it's a sink. So it's very much in the interests on the whole of countries which belong in the tropical zone and often are at least less developed to have a better understanding of their land use emissions. And it's usually in those countries where the survey capacity and the sample capacity to do that in situ is very poorly understood. Less well developed. There's a very good analogy with RED, and I worked for many years on a project, amongst other things, which is called the Global Forest Observation Initiative, which was to provide wall-to-wall coverage of satellite data for countries to provide to the inventory agencies for countries to be able to give them validated authoritative statements about the status of their forest, which would allow them to make claim payments again under the RED+ scheme.
Oh, fantastic. Because that was another question, which was how much is payments, results-based finance, already impacting the availability of resource for this type of assessment, and what things are counted? But that's a later question, Stephen, but you've partially answered it, so thank you.
I think the whole question of climate finance, particularly when it comes to individual projects and so on, is another completely different question. How you monitor that, it's less to do with emissions, it's more to do with the impact on the ground of whatever it is countries are supposed to be doing in order to claim their carbon credits, whether that's extending forest extent or whatever it may be. That's another question which is a really thorny one. There's an awful lot of nonsense talked about it. There's an awful lot of greenwashing goes on. And there is some good work which is being done. But the fundamental basis for all this has to be objective, verifiable evidence of what's happening.
Thank you.
They're related, but they're slightly different questions.
Yeah. Thanks. Orlando, do you want to ask the last question?
Okay, I can read Orlando's just about if I get my glasses. I look at another screen. The methods to make the expansion of existing nets as efficient as possible. Oh, I see. I guess you mean by that to redistribute the locations of the sensors to the for an optimal sampling strategy. No, not really. Because the individual measurements are the responsibilities of national agencies, they will either do it or they won't. You will get countries where one developed country may well subsidize the provision of measurements in another country, a less developed country. That happens, but what we're trying to do that globally is through this Global Basic Observation Network, GBON, which would provide an international framework of funding coming from the World Bank through UNFCCC, which would allow a central fund to distribute the observation networks optimally. So I guess in some sense we're moving to that, but it's not a matter of removing some stations and placing them elsewhere. It's enhancing the overall global contribution.
Okay, great. With that, thank you so much, Stephen, for your excellent talk. I think the video is not going to be something anybody's going to forget anytime soon, but also the wealth of information behind it. I wonder if you can ask you for a copy of the slides, because I think you have citations to many other things.
Well, it's about 200 megabytes, but I will somehow find a way of getting them to you. I'll tell you a bit and throw away some of the hidden slides which are in there and so on. But
Okay.
it's an enormously complex question. It's one of the most difficult questions which we can address. And I think it's a very important one, and it's one that I'm very happy to be spending part of my time working on. But it's not something that I'm in both feet with, as it were. It's just something that I'm sitting on the sidelines with this question.
Anyway, well, thank you very much. And for those people on the call, I'm going to stop recording now, and we're going to switch into sort of the EEG group meeting. And so